Check if it works.
Refresh.
Oh, wait.
Let me show me muted. Yeah.
I think it's good, yeah.
Yeah, cool.
Cool. I think we're good. Should be fine. Wait, so, Jerry, sorry. This is all. Wait, I exited the stream by accident. Can you get back on the stream by accident?
You did? Okay.
Yeah.
This closes, I think. Oopsies, okay. Oh, it's a history.
Yeah, just go in there. Check.
This is what I'm doing.
Yeah.
Okay, doesn't matter.
Just check if it works. So.
Yeah.
I was trying to get the chat.
Yeah.
Okay. Good. All right. Okay, can everyone hear me? Is the mic working? Yep. Okay. We're going to get started now. So thank you everyone for coming to our ELEC1111 Crash Course. So in today's crash course, we're going to be going through your 4 topics. It will be happening in your midterm, which are circuit basics, Kirchhoff's laws, circuit theorems, and capacitors. So could you all take a moment to scan this QR code? It's so we can record how many people actually show up to our crash courses, and also so that we can get money from ARC. And so I'll just leave that for about 30 seconds. If you just came in, could you please scan the QR code so that we can record attendance? Okay. Okay. We can get started in 10 seconds. Okay. So we're going to start with circuit basics. So here's some key content points. So first of all, we have Ohm's law here, which is, surely everyone should know this from high school. V equals RI, so you can use it to find the voltage drop across resistors. And next point, we have power. So power is given by your voltage times by the current going through that element. And you can use this for any element, including sources. And then if you apply Ohm's law into the power equation, you can also get these 2 alternatives. Okay, equivalent resistance. So if you have if you have multiple resistors in a series layout, so something like this, you can simplify this into one resistor, and the resistance of this new resistor will be equal to the sum of a resistance. And likewise in parallel, if we have two resistors in parallel, you can simplify this down to just one resistor, and the resistance of this is given by the sum of the reciprocals, and then you flip it again. So 1 over the sum of the reciprocals. Now, a few more points is for short circuit, it's basically when you have a branch that has 0 resistance. So for example, if we have a resistor here, and we also have just another branch with no resistance here, and we call this over here a short circuit. So in this case, the voltage drop across these 2 points would be 0 because all your current is flowing through here and there's no resistance in between. And on the other hand, we have open circuit, which is basically where there's infinite resistance in between. It's kind of like a disconnection in the wire. Okay, and then yes, no current would flow through here. Okay, any questions? Okay, we're going to move on to this question. So in this question it says, the max current that can flow through each diode without break-in is 50 milliamps. Determine which LEDs will light up and find the power dissipated by each of them. Okay. Okay, so to start off with this question, let's put in our ground node over here. So to start off with, the ground node is 0 volts here, so we know that from the voltage source over here, we're going to have 3 volts at the top over here. So at this point, our voltage will be 3 volts. Now, for LEDs to function, the voltage drop across them has to be greater than the forward voltage. So if it's less than the forward voltage, the current will not flow through the LED. So what I mean by forward voltage is this voltage here. So let's check the first branch to see if current will flow through here and the LEDs will light up. So to do this, we can have a look at these two LEDs combined. So one of the LEDs has a forward voltage of 1.7. So that means between these two LEDs, you're going to have a voltage drop of 3.4 volts. And now the battery, this voltage source only supplies 3 volts. So if we drop 3.4 volts, we're going to end up with a negative voltage. So in this case, no current is going to go through here. Oops, sorry. No current will flow through here because the voltage is less than the forward voltage. So you can ignore that branch. So we know these two won't light up. Okay, let's have a look at the second branch. So in this case, we only have one LED, and the voltage drop across that is 1.7. And we have 3 volts, so that's enough that our voltage is greater than our forward voltage. So yes, there will be current flowing through here. I'm going to call that I1. Now, one other thing it says is that each diode can handle a maximum of 50 milliamps. So let's check if the current flowing through that branch is not greater than 50 milliamps. So to do that, we can use Ohm's law with this resistor here. So we can do I1 equals the voltage drop across this resistor, which is, so we have 3 across the whole branch, and we know that 1.7 voltage, there's a drop of 1.7 volts here. So in this case, we would have a drop of 1.3 volts for this resistor. So we have V on the resistance of the resistor, which is 50, and that should give you 26 milliamps. Now that is less than 50 milliamps, so we're safe. So current will flow through here, this LED will light up without break-in. Okay. Now, Let's have a look at the third branch. So in this case, we also have one LED, which is down here, and we also have a resistor. So since the voltage drop between these 2 points is greater than the fold voltage, this LED will light up. But let's check if the current flowing through that is greater than 50 milliamps. So you can apply the same process. So at this point, we know it's going to be 1.7 volts. So the drop between these two nodes here will be 1.3 volts. And then if we apply Ohm's law again, we'll call this out 2, we get a drop of 1.3 over, in this case, it's only 1 ohms of resistance. So for this case, you'll get 1.3 amps of current. And that is a lot greater than 50 milliamps. So this is greater than 50 milliamps. And that means that the LED will break. So in this case, this branch is also gone, because no current is going to flow through it. Okay, so we only have one branch that works, and we're trying to find the power dissipated. So if you remember, power dissipated is given by the voltage of the element multiplied by the current. So we know the voltage drop across this diode is 1.7. And the current through here, we calculated from this over here, which is 26 milliamps. So 26 times 10 to the minus 3 amps. And then if I put that in the calculator, we should get 44.2 milliwatts, okay? So that's the first question. Make sense? Okay. All right, let's move on. So that's pretty simple. Okay, let's have a look at Kirchhoff's laws. So this will be topic 2. Okay, so these two are Kirchhoff's laws. We have KVL, which is Kirchhoff voltage law. It states that if you have a circuit and you have a few elements, let's say we have a source here, a resistor here, and let's say another resistor. If you calculate the voltage drop across, if you sum up the voltage drops across each of these elements in a loop, you'll get 0. And then we have Kirchhoff's circuit law, current law, which is if you're given a node, so let's say at this point, where current will split, the current that enters here, we'll call this I1, and let's say I2 is leaving and I3 is leaving. The current that enters the node is equal to the current that exits the node. So in this case, it would be I1, which is entering, is equal to the sum of I2 and I3, because these two are leaving the node. Okay? And then we can use KVL and KCL to do nodal and mesh analysis. I'll cover that in some examples later. Now, I'll talk about voltage division. So if you're given a set of resistors or elements in series, let's take a look at this one. We can calculate the voltage drop across each of these resistors. So let's say you're trying to find the voltage drop across V2 over here. What we would do is we would find the total equivalent resistance, so REQ. So I'll just call this R1 here, R2. So REQ would be the sum of your resistance in this case, which is R1 plus R2. And then we can apply voltage division, which says the voltage drop across that particular element is the voltage of the source, so of the whole circuit, multiplied by the resistance you want to find. So in this case, we want to find V2 here. So we want to use R1. And then you divide it by the total or equivalent resistance of your circuit. So in this case, if you want to try and find the voltage drop V2, we would do V1, which is the voltage of the source, multiplied by R1, which is the resistance of V2, over your equivalent resistance, which is R1 plus R2, okay? And then likewise for current division, it's the exact same thing, but your equivalent resistance is flipped. So it would be your equivalent resistance over your the resistance of that element or that branch you're trying to find. Okay? All make sense? Cool. Okay, let's move on. We're going to try this question here. So for the circuit shown below, apply nodal and mesh analysis and write down the nodal equations. Okay. So to start off with, we're going to do nodal analysis. Okay. Yep. So the first thing we can do is, if you ever see a voltage source that doesn't lie between, if it lies between two non-ground nodes, so in this case there's a node here, and this is a node here, you have to establish a supernode, okay? So in this case, the ground node's all the way down here. So this is where it's 0 volts, but the voltage source is up here, so we have to make a supernode. So the way we do that is, before we do that, let's actually label our points. So I'll just call this node here V1, and I'll call this V2. I'll call this V3 over here. So we're just going to label all our unknown nodes, okay? So we know that the voltage at the bottom is 0. So we can just call this point 0. Okay. Now, before we go further, let's also label the polarities of our resistors. So it doesn't matter which way you do them, just the math will work out. So I'll just do this. Then let's do that. So, okay, let's do our supernode constraint equation. So we're given that the difference between V4 and V3 is 2 volts. Now, you have to make sure we know which one has a higher voltage. So if we look at the voltage source, we know that the current's going this way, from negative to positive. So we know that V3 is actually greater than V4. So our supernode constraint equation would be V3 minus V4 is equal to 2 volts. So that gives us one of our equations we can use to solve. Okay. Now, to do nodal analysis, we basically apply KCL at each unknown node to get equations, and then we can solve them simultaneously. So let's try this at node 1. But before we do that, we have to label all our currents. So in this case, our current is going from positive to negative for resistor, so we'll just call that one I1. And I1 is entering this node. We'll call this I2, leaving this node. Now for this branch, we know the current because it's given by the current source, okay? So 3 amps must flow through this branch. So we know that's 3 amps there. The same thing here, 3 amps must flow into V2. And we're going this way, so we'll call that I3. We're going that way, so we'll call it I4. And then same thing here. Since this is the same current, we can just write I4 here. Now, in this case, we have I2 going up here, and it'll come back down, so this is still I2. And then this one, we're not sure, so we'll just call it I5, okay? So let's apply KCL at V1, which is here. So what we should get is the current going in, which is I1, is equal to the sum of the current leaving the node, which is I2 plus 3. Now, what we do now is we use Ohm's law to rewrite our currents in terms of our voltage and our resistance. So in this case, I1 is given by the voltage drop across your 1 ohm resistor. So in this case, we have 0 volts here. So our voltage drop would be 0 minus V1. And now we have to divide that by the resistance of that element, which is 1. So I equals V on R from Ohm's law. Voltage drop is 0 minus V1. Now the direction matters, so just keep in mind. And then over the resistance, which is 1 ohm. Okay, so if we do the same for I2, we have the voltage drop is V1 minus V4. And the resistance is 2 ohms. Let's write that down. And then we can leave 3 as 3. Now, let's just simplify this a bit. So the easiest way I think I like to do it is I try and get rid of the denominator. Just try and get rid of the fractions, so it's easy to work with. So let's multiply everything by 2. So on the left-hand side, we'll get minus 2V1. Right-hand side, we'll just get V1 minus V4 plus 6. Now, so we don't have any fractions left. Let's simplify this a bit. We'll try and write it in terms of have all our voltages on the left and our constants on the right. So in this case, we would have, if we simplify this, we should get minus 3V1 plus V4 is equal to 6. So that gives us one of our equations. And that's okay. Cool. Now, let's try KCL again, but we're going to do it at a different node. So let's try at V2. Okay. So in this case, we have our 3 amps going into V2. We have our I3 going out and also I4 going out. So equation here would be 3 amps is equal to I3 plus I4. Okay, and then we do the same thing. We can rewrite I3 as V2 minus 0 over 4. So V2 minus 0 over 4. And then same thing for I4. We can do V2 minus V3 over 3 ohms. Okay, and let's simplify it. So let's multiply both hand sides by 12, which gets rid of the fractions. So we should get 36 is equal to 3V2 plus 4V2 minus 4V3. And then just rewrite that in the better way. We should get 7V2 minus 4V3 is equal to 36. Okay, so that's another equation we can use. And now we have to do KCL one more time because we have 4 variables. So we have V1, we have V2 over here, we have V3, and we also have V4. So we need a fourth equation so that we can solve simultaneously. Now, let's try KCL at the supernode. So since we have a supernode over here, we can actually form a supernode. So basically what that is we combine the 2 nodes, V3 and V4 together, and that gives us our supernode. Now, we basically do the same thing, and we apply KCL to the supernode, but we just treat the 2 nodes as one single node, okay? So what's the current that's going into the supernode? Well, we have I2 going in here. We also have I4 going in here. And then we have I5 leaving the supernode. So in this case, I'll just write it here. So that's supernode. We have I2 plus I4 is equal to I5. Okay. Cool. So we can rewrite I2 as V1 minus V4 on 2. I4 we can rewrite as, from before, over here, we have V2 minus V3 on 3. And I5, if you have a look, we can rewrite this as V3 minus 0 here over 2. So V3 minus 0 over 2. Now if I do the same process, I'm just going to go to what you should get. You should get 3V1 plus 2V2 minus 5V3 and minus 3V4 is equal to 0. And now we have 4 equations, we have 4 variables, so we can solve this. But it's pretty tedious to solve, so I'm not going to do that. So I'll just give you the equations. I'll just give you the solution. So we should have V1 is equal to 90 on 41. V2 is equal to 244 on 41. V3 is equal to 58 on 41. V4 is equal to minus 24 on 41. Okay? So does that all make sense? Any questions? Yep. Yep. This one? Well, so that's the supernode, right? So we did that at the very start. We know that the voltage difference between V4 and V3 is 2 volts, right? It's because of the power supply, right? Does that answer your question, or? Yeah. Okay, yeah. Cool. Any other questions? Yep. You have access to the live stream recording. You can, yeah. But okay, because I might rub this out. I might just copy this, because I'm also I'm just gonna copy this, because I'm gonna rub this all out. We're gonna do mesh analysis for the same question. Okay. Yeah. Okay. Okay. Let's move on. Okay, let's do the same question, but we're going to do mesh analysis, okay? So in this case, now, before we do this, there's a few important rules I like to follow, and this is to make sure you can always get the correct answers for mesh. So this is the easiest way I find. So what we do is label all meshes going clockwise. So let's do that. We'll do clockwise here. So let's call this, I'll call this I1. We'll do this mesh here, I2, and we'll do this mesh here, I3. So mesh is a small slip in a circuit. Now, the next thing we do is start from the lowest mesh, so I1, and assign polarities in all the elements. That ensures the lowest current always goes from positive to negative terminal. So what I mean by that is we have a look at I1, and we look at a element. So in this case, we have the 1 ohm resistor. We always make it so that it goes from positive to negative. So current in this case is going up here. So we want positive to negative here. And in this case, we have positive to negative here. And then we continue for the next lowest mesh, so I2. And then we do the same thing. But we do not touch the ones we've already done for I1. So let's go around. We'll do positive to negative here. And we'll do positive to negative here. And then we'll do I3. So we've already done that one. So we'll just do positive to negative here. Okay, all makes sense? Now, before we do anything, we also have a current source here. So our current source here is between 2 meshes. So what we have to do is create a super mesh. And basically, our constraint equation is given by the difference of the current is equal to the current source, okay? So we know I1 is going this way, and I3 is going that way. So if we do I1 minus I3, we should get 3 amps. Okay, so that's one of our equations we can use. Now, okay, now we can apply KVL around each mesh. But before we do that, let's actually create our super mesh. So super mesh kind of goes around I1 and I3 now. Okay, so let's do KVL at I2, okay? So what we do is rewrite the voltage drop of each element in terms of the current going through it and the resistance of it, given by Ohm's law. So let's do KVL at I2. What we should get is, we're going through, let's just go through here. Let's go from here. We're going through the 2 ohm resistor, and we have I2 going through it. So the voltage drop across here would be 2I2, okay? And then we're entering the 4 ohm resistor from the negative side. So every time you enter something from the negative terminal, we have to put a minus sign, okay? So it will be minus. Now, the resistance is 4, but the current going through this 4 ohm resistor is actually I1 minus I2, which is the net current. So we have I1 minus I2 here. And then the 3 ohm resistor here, it's plus 3, but the current is actually I2 minus I3. So the way we've set this up by doing all that steps here is so that whenever we have a resistor between 2 meshes, we can always just do the lowest minus the higher one. It would always be that case. Okay? So a KVL states that the sum of voltages is equal to 0. So we have that equation. Now, if we simplify this, we should get minus 4I1 plus 9I2 minus 3I3 is equal to 0. Now, we only have three unknown variables, I1, I2, I3. So we just need one more equation in this case. So let's do the KVL at the super mesh. So we're going to go around this entire mesh. So let's start from the bottom left. We have our 1 ohm resistor, so it's just I1, the voltage drop. And then we have up here the 2 ohm resistor from I3, so it's plus 2I3. Now, for a voltage source, the voltage drop is just the source of that the voltage of that source. So in this case, we're going through the negative terminal, so we have to include a -2 here. And then we have the 3 ohm resistor. We're going in from the negative terminal. So minus 3 I2 minus I3. And then the 4 ohm resistor plus 4. And we have I1 minus I2. And all of that's equal to 0. And if you simplify this, we should get 5 I1 minus 7 I2 plus 5 I3 is equal to 2. Okay? So that's our 3 equations. And you can solve them simultaneously. I'll just tell you the answer. We should get I1 is equal to 90 on 41. I2 is equal to 29 on 41. I3 is equal to minus 33 on 41. Okay? Make sense? Yes?
So for the voltage source as well, when you enter through the negative terminal?
Yes. Yes, it's just whatever you enter. If you enter from a negative terminal, it doesn't matter if it's a resistor or a source, you just have to put a negative sign.
Does it work for dependent mesh loss?
Yes, it's the same for dependent. Okay? Any more questions? If not, let's move on. So I've gone over that. Okay, let's do one last question. Same thing, we're going to do nodal and mesh analysis, but this time we have dependent sources, okay? So it's going to be a bit harder. So dependent sources are basically gives a voltage or current output dependent on a current or voltage or something else in a circuit. So in this case, your current source and your voltage source is given by the current flowing through here, okay? So we can basically apply the same process here. But we just have one extra variable, IA, to worry about. Okay, so let's start with nodal analysis. So remember, first thing we do is label our nodes. So we'll call this V1, we'll call this V2. And now this node up here, we know that this is 0 here. And we have a 5 IA voltage source over here. So now our voltage up here would be 5 IA, okay? Makes sense? Now, we have to label our polarities. So we'll do just that, like that, We'll do it that way. Okay, so it doesn't matter which way you label them. And now, what does matter is the direction of your current. So we'll call this going up here I1. Now, the current going this way is just IA from here. The current going up here is I2, okay? Now, yeah, over here, we have I2 going here, from here. We'll call this, we don't actually need that, it's fine. The current going through here is actually the current source here, which is 100 IA. Now, let's right here, 100 IA as well. We have IA going in here. And then we'll just call this I3, okay? Okay, makes sense? So let's do, before we do our KCLs, we also have a supernode here. So let's combine these two nodes together. And basically, let's write our supernode constraint equation. So we have V2 is greater than V1. So we have V2 minus V1 is the voltage of the source, which is 3. Okay? Now, let's start by doing KCL and let's start with the supernode, okay? So for this case, we have I1 entering the supernode. We also have 100 IA entering the supernode. So let's write that. So I1 plus 100 IA is equal to. And now we have I2 leaving the supernode up here, and we have I3 leaving the supernode over there. Yeah, so it would be I2 plus I3. Okay? And then we write I1, I2, I3 in terms of our voltage drops and resistance. So I1 would be 0 volts here, 0 minus V1 over 2. We'll leave IA as it is. And then I2 would be V1 minus 5 IA over 1. And I3 would be V2 minus 0 over 5. Okay, if we simplify this, we should get minus 15 V1 minus 2 V2 is equal to negative 1050 IA. Okay, so that gives us one equation we can use. And then let's do it one more time, because we have V1 and V2, but we also have IA. So we actually we need one more equation. So let's have a look at this diagram. We could do KCL at this point, but we're not sure what the current going in here is, right? Because we only have a voltage source, it doesn't really tell us what the current is. So we can't really do KCL at this point. But what we could do in this case, we're trying to get an equation with IA. So we could actually go into one of these nodes and do KCL just at one of these nodes. So let's try V1, okay? So for V1, we have the current going in is I1. The current going out is I2 and IA, okay? So I1 is equal to I2 plus IA. We do the same process. I1 from before was 0 minus V1 on 2. I2 is V1 minus 5, IA over 1. And then we have IA, okay? Yeah, so now we have another equation with only V1 and IA. So we can solve this. We can simplify this down to this. And basically, now we have 3 variables. We have V1, V2, and IA. And we have 3 equations, so we can solve them simultaneously. I won't do that as well, so I'll just tell you the answers. V1 is 24 on 1507. V2 is 4545 on 1507. And your IA would be 9 on 1507. Okay? So you can just do that by solving this Okay, make sense? Any questions? If not, okay, let me just copy this. Oops. We'll move on to do the same question with mesh analysis. Okay, wait. Oh, sorry. This is weird. Okay, we'll just move this over here. Okay. So now, let's do the same thing, but with mesh analysis. So from before, let's label our meshes going clockwise. So we have I1 here. We have I2 here. And we have I3 here. So we have a question in the chat. Can we treat node V3 as 2 volts? V3 was, do you mean from the question beforehand? From this one? Sorry, let me just see. In this case, yeah, I think you're talking about this. If this was V3 here, we can't really treat it as 2 volts because we're not sure what V4 up here was. If we know what V4 is, we know that V3 is just whatever V4 is plus 2 volts. If we know that V4 is 0 volts, then we know V3 is 2 volts. But we're not sure what V3 exactly is. Okay? Hope that answers your question. Okay, let's get back to this. Okay, let's label our polarities. So always start with I1. We're going to go from positive to negative. Let's continue from I2. So plus, minus, plus, minus. And then we have nothing else to label for I3. Okay? So now what we do is, sorry, I'm looking at the wrong thing. Okay, we have a super mesh here, which is this current source here. It's between I2 and I3. So let's do our super mesh constraint equation, which is I2 minus I3 is equal to 100 IA. Okay? So we'll leave that as it is. Now, let's do KVL. Actually, let's label the super mesh. Here. So let's do KVL at I1, which is this one down here. So we have I1 going through the 2 ohm resistor, so we have 2 I1 as a voltage drop. Now we're going in through the negative terminal of this voltage source, so we have minus 3. And then we have plus 5, and then the difference of the currents, which is I1 minus I3. And that should all be equal to 0. Simplifying this, you should get 7I1 minus 5I3 is equal to 3. Okay? So that's an equation. And then we can do KVL again. Let's do it around the super mesh. So in this case, we have, let's start from here. We have I2 going through the 1 ohm resistor, which is just I2. And then we're going through the positive terminal of the dependent voltage source. So we have plus 5IA. We're going through the negative terminal of the 5 ohm resistor, so negative 5. And we have I1 minus I3. And then going through the positive terminal, positive terminal of the 3 volt source. So plus 3, and that should all be equal to 0. Okay, and then same thing, we simplify this down. We should get this. Now, we have I1 here, we have I2 here, we have I3 here, and we also have IA. Okay, so we have too many variables, but we only have 3 equations, right? And when we're out of meshes to do KVL. So what can we do in this case? Well, we can kind of find what IA is in terms of our meshes. Okay, So we know that IA is this, right? IA you can rewrite as your current going here, which is I1, subtract the current going this way, which is I2. Okay? So we can write a fourth equation, call it the IA equation, which is IA is equal to I1 minus I2, okay? I1 minus I2 gives you IA. Now we have four equations. We can solve this, so I'll just tell you the answers. You get I1 equals negative 12 on 1507. I2 equals negative 21 on 1507. I3 is negative 921 on 1507. And then IA is 9 on 1507. Okay? All makes sense? Yes.
If you can do super mesh analysis, is it always also possible to do super node analysis, or is one usually better than the other?
Okay, yeah, so for this question, we have a super node and a super mesh. So because the ground node is over here, we can't really change where that is. So we have to have a super node if we do nodal analysis. If we do mesh analysis, since we have this between two meshes, we have to have a super mesh. So in this case, we can't avoid either super mesh or super node. Sometimes you might get, let's say this current source was not there. So in this case, if you do mesh analysis, there's no super mesh, okay? So it'll actually be easier to do mesh analysis. But what you mainly want to look for to see which one's easier is you want to see how many equations you would end up with. So for this case, when we did nodal analysis, we actually had we only had 3 equations, right? As opposed to when we did mesh analysis, we had 4 equations. So this is actually harder to solve, okay? Yeah, so that's just a tip, okay? Any final questions before I move on? Nope. Okay, I'm going to hand over to Jerry, who will continue with circuit theorems. Okay.
Okay, so welcome to our next topic, which is circuit theorems. Before we actually get on this topic, let me just put a fun brain teaser, which I hope it's interesting. So assume we have an infinite network like this. So assume this network continues, right? And then it goes towards infinity. All the resistors are 1 ohm. So very nice number. The question is, if it's not RTH, this is more REQ. What is going to be the equivalence resistance as seen from those 2 terminals? So you guys might want to just have a think of this right now. It's probably going to be a little challenging, but it's pretty interesting, and I'll come back to this later. So does the answer convert to some fixed value, which is nice? Or does it convert to some random number we never knew before? Or does it all diverge? So maybe just have a little think about it. But now, for the sake of this crash course, let's go back to our actual topic, which is circuit theorems. In circuit theorems, we really only have 4 topics. The first being superposition, second being source transformation, and then third being Thevenin/Norton. But this is the actually larger topic, which can be split really into 2 subtopics, which is first finding VTH and IN, and second finding Thevenin resistance. And to find Thevenin resistance, there's actually 3 methods. I'll get to it later. And for maximum power transfer, it always accompanies Thevenin circuits, I think. So you always get a question like part A, find Thevenin voltage, part B, find Thevenin resistance, and let's say part C, find the maximum power transfer. In maximum power transfer formula, and it might be a little difficult to prove for some people. So I'll present a quick derivation of it just in case we forget it during the exam. If I've done 1A, I think they gave you this question in your assignment, right? And they asked you to find it by differentiating. But then this might be like too slow of a method during the exam when like we don't have that time. So let me just present a much quicker method. So suppose we have a Thevenin's equivalent circuit like this. So that's VTH. And you have a RTH here. That's RL. That's RTH. That's RL. To find the power observed by RL, I recommend finding I first. So I equals to VTH on RTH plus RL. And so P equals to I square R. L equals to RL VTH squared on RTH squared plus RL whole thing squared. So this is our expression for the power observed by RL in general. But to find the maximum power that can be observed by RL, our first method is to just set RL a variable and just start differentiating it. The other method, which is quicker, is to use the AMGM inequality, as you should have heard of it if I've done for you in high school. So basically, AMGM inequality states that if I have two variables, two real numbers, actually x, y, we have x plus y is greater or equal to 2 root xy. So yeah, and the equality holds, of course, when x, y are equal. So left-hand side equals to 2x, the right-hand side equals to, well, 2x again. We can apply it to actually our denominator here. So using the AMGM inequality, we have AMGM. We have RTH plus by RL whole thing squared is greater or equal to 2 root RTH RL squared, which actually equals to 4 RTH RL. And you can just now sub it back in here. So sub it back in our denominator. We have P is actually less or equal to, because well, we're actually making the denominator like smaller in this case. So P actually gets larger. P is less or equal to RL VTH squared on 4 RTH RL, which equals to VTH squared on 4 RTH. And the answer just pops out like this. And remember, the maximum power holds out RTH equals to RL, because that's when the inequality, so this one, holds. So yeah, is there any questions regarding the theory before I jump to actual examples? I'll elaborate on each of those theories during the example. So cool. Let's look at our first example, which is Thevenin question. Just to make everything clear, like everything that's presented in the image is meant to be within the terminals AB, so including the 6 kilo ohm. Cool. And the question just asks us to find the Thevenin voltage. So we want to find the open circuit voltage of A and B. So VTH equals to VA minus VB. In this case, it's very good because it's already open circuited. So let's begin. So to find Thevenin voltage is really only one way, which is either do nodal or mesh, as what Ben said before. In this particular case, I think it would be easiest if we actually ground VA. So this, I'll make it clear. So if you ground VA, so this is now a ground. Now this node is 10 volts. You can name this Vx, and you can name this Vb. And the VTH just becomes minus Vb. It just makes our calculation much more convenient by looking at this. So to do nodal analysis, we'll just do what Ben has done before. So let's label some currents. Oh, by the way, I0 is meant to be this. Sorry, I0 is meant to be here. So that's what and this is I0. Cool. And so let's label our other currents. That's I1, that's I2, that's I3, that's I4. Of course, the currents are just labeled arbitrary, so there's no particular order we have to label them or direction we have to label them. So looking at this diagram, the first thing we probably can do first is to find I0, right? If this is 10 volts, I0 is just given by 10 ohms 300 according to Ohm's law. So we can have I0 equals to 10 ohms 300. That should be a 10 ohms 300 equals 130 amp. So now for I0, we know that's going to be 2 ohm 15 amp. So now it's going to be much nicer. So let's label it here, 2 ohm 15 amps. And now let's actually do the nodal analysis. We have the easiest two nodes to do it is actually Vx and Vb. So let us do nodal analysis Vx first. So KCL in Vx. We have I1 plus I2 plus by 2 ohm 15 equals to I3. Why? Because I3 is the only current that's leaving the node. Well, I1, I2, and 2 ohm 15, so entering the node. And KCL basically states that current entering a node equals to current leaving a node. So we have this expression here. Now let's express all those currents in terms of voltage. So I1 equals to 10 minus by Vx on 100 plus by I2 equals to 10 minus by Vx on 200 plus by 2 on 15 equals to I3. I3 equals to Vx minus Vb on 100. As you can see, this might not be the best or the clearest expression ever because we have to solve simultaneous equations using this. So every time if you get something like this during the exam, I really recommend to slow down and just try your best to avoid these silly mistakes. So if I've done this slowly and correctly, the expression should be simplified to 170 on 3 equals to 5Vx minus by 2Vb. Let's label this one. And our other KCL is our Vb. So let's do it. KCL in Vb. We have the current entering the node is I3. Current leaving the node is 2 ohm 15 and I4. So we have this expression here. I3 we have basically look at it previously is Vx minus by Vb on 100 equals to 2 ohm 15 plus by I4 is just given by Vb minus by 0 on 6,000. So Vb minus 0 on 6,000. Again, not the clearest expression, despite better than the last one. If I have simplified it correctly, we should get the expression 800 equals to 60 Vx minus by 61 Vb. And let's label it 2. 2 variables and 2 equations. We can now just solve them easily. I mean, but still be careful with the numbers because it's not the best numbers. If I have solved the simultaneous equation correctly, so solving 1 and 2, we should get Vb equals to minus 3.24 volts just by solving 1 and 2. And look at and we have determined the expressions for VTH here. So now VTH equals to 3.24 volts. We'll be using this number later, so let's just quickly box it. Yeah, and this is basically how we do every Thevenin voltage question. Find the open circuit voltage using either mesh or nodal. Is there any questions regarding anything I have done here? Yes?
I've learned before when finding Thevenin voltage that you can treat the low resistor as an open circuit and then solve that way. Is that true or not
Yes, sorry, so which?
I've done Thevenin voltage equivalents where you treat the, so for example, the 6K ohm,
Yeah.
Which is the load in this example, right?
Oh,
And you treat it as an open circuit. Does that work?
so this, I think this is an exam question, but it's not really drawn too well. Yeah, 6K is meant to be interior to the Thevenin network. So yeah, it's not actual load resistance. It's inside there. Yeah, cool. Does that answer your question? Yeah. So basically, if you have something else attached like here, okay, wait. Yeah. Yeah, cool. If I have something else like attached like here, then we open circuit this. Cool. So any other questions? Cool. Let's move on to the next question now. The next part is actually when we get much more freedom. As we have said before, there's actually 3 methods to do this, to find the RTH. These 3 being, I'll list them out now. The first, we do just source transformation and just hope for, and just pray that it actually simplifies. But unfortunately, like, I think this barely works, so in this case, it's not going to work right. Let me label I0 here. In this case, if you actually try to do source transformation, then we lose information about I0. So unfortunately, it's not going to work. Our second method is to add a test voltage source or test current source across AB. So if I have terminals AB here, wait, let me write it here. A test voltage / current source across AB. So basically, we do something like this. And of course, we short circuit any voltage source we have here, which is 10 volts. So that works. But the third method, I think, is my favorite method, which is to find the short circuit current and basically Norton current, and find RTH from there. So SC stands for short circuit. By short circuiting AB and RTH equals to VTH on IC. So I think this method is better just because we don't have to come up with our test source, but like both methods could work, and like one method might be easier than another method in particular questions. In this case, I think both are similar in basically difficulty. So I'll use the third method here. I'll use this. But just for you know, if you want to do second one, it also works. So let's short circuit this. As you can see, if you short circuit AB, then the 6 kilo ohm will also be short circuited, right? So let's just remove the 6 kilo ohm over here. And now if you actually short circuit 6 kilo ohm, we can actually we have 2 parallel wires, right? We can just treat them as one. So just remember that if you short circuit AB, then the 6 kilo ohm resistor will be short circuited. We want to find the IC, so ISC. Let me label this as with blue, just for consistency. So that's ISC. And let's just have the same labels. So that's I1, that's I2, and that's I3, and that's 10 volts. And let's just ground VA again, just for convenience. As you can see, if we ground VA again, then I0 is again just 130 amps, same as before. And so for I0, it's going to be 215 amps. So nothing has changed from previously, from our previous part. And even better, let me label this as let me label this as Vx, label this as Vb. So even better, we see so KCL in Vx, we have I1 plus by I2 plus by 215 equals to I3, which is actually the same expression as what you have here. So our final one actually still applies in this case. So let's just copy it here. 170 on 3 equals to 5Vx minus 2Vb. But then what's Vb? Do you see, like, if you short circuit this 6 kilo ohm, then Vb is at the same node with the ground. So Vb is actually 0. Wait, let me just write this in black just for consistency. So 170 on 3 equals to 5Vx minus by 2Vb equals to 5Vx. Because Vb is 0, we have grounded to be so. And by doing that, we have Vx equals to 34 ohms, 3 volts. After we have Vx, we don't actually need KCL in another node, in node B. So because basically, well, I'll explain it later. So let's find I3 first. Do you see, like, we can apply Ohm's law on I3. So here, Ohm's law here. I3 equals to Vx minus by Vb on 100, which is equals to 34 on 3 minus 0 on 100, and turns out to be 117 on 150 amps. Cool. Now we have I3, right? We can do another KCL. But just remember, KCL doesn't only apply to nodes. It also applies to any closed surface in this circuit. So, for example, in this closed surface, right? If you just draw any closed surface, let's say here, KCL also applies to this closed surface. So the current entering here equals to current leaving here. What's the current entering here? So wait, let me just say case. Let me just rub this out just for clearer. So that's our closed surface. Right. So KCL in closed surface, I would write it in green just to say that we have done in green in closed surface. We have ISC plus by I3 equals to 2 on 15. Cool. So ISC equals to 2 on 15 minus by 17 on 150. And it actually simplifies out to be like very nice. So the ISC equals to 0.02 amps just by chucking it in calculator. It just says 2 milliamps, which is very nice. So now we have ISC, right? We also have VTH from here. We can now calculate the Thevenin resistance via RTH equals to VTH on ISC. If we chuck it in calculator, we should get 162 ohms. And that's how we can find RTH. So any questions regarding this question? Because finding resistance, I personally think is harder than finding VTH. So all good? Yeah. Yes, sir.
Why did you change the direction of the short circuit current?
Oh,
Instead of going to the left.
oh, short circuit.
The ISC instead of going to the right.
Okay, so let me explain.
And the other example says go to the left. It's I4 going to the left.
Oh yeah, other one I just labeled it I4. I could just label I4 like here. It doesn't really matter which direction I label it. Cool. Yeah. Also, yeah. Sorry.
How did you get anything
VX. Okay, so cool. So if you look at our node in VX, right? You see I1, I2, and 2 on 15 is entering the node, and I3 is leaving it. Yeah. So current entering a node equals to current leaving a node. We have this, right? And then do we see like how this is same expression as this? It's actually the same thing, and yeah. So the result here actually applies here, because we actually didn't change anything regarding this node, right? Yeah, cool. Yeah, good question. So any other questions? Cool. Let's move on then. The next one is probably the easiest one, which is finding maximum power transfer and the load resistance that will result in maximum power transfer. Remember, we have proven from AMGM before that Pmax happens at, so RTH equals to RL. And RL we have determined it to be 162 ohms. So this equals to 162 ohms. And this Pmax equals to VTH squared on 4 RTH. It's also the formula we have proven previously. So VTH is 3.24 squared on 4, 162. If you chuck it in calculator, we should get 16.2 milliwatts. Again, this is probably going to be easiest part of the exam, just chucking in formula. So cool, can we move on to the next question? But by the way, so like this setup is, I think it's pretty classic for an exam. So find the VTH, find the VTH first, then find the RTH. And then we find, we find the maximum power transfer. So just make sure you guys know how to do this. But now, so that's the most standard question. Now let's look at this question. So it might not be the most standard one as what you expected, but it's a pretty nice question. So basically we have this circuit over here, right? And the bottom is ground. Is it possible for us to choose a positive Rx such that Vx is independent of RL? So no matter how we change RL, the Vx stays the same. Just out of curiosity, how many of us think yes? Yeah. And how many of us think no? So unsure, it's okay. It's all good. So let's look at this now. Again, so by looking at this circuit, do we see like there's nothing connected to A and B, right? So the 2 kilo ohm and the RL is actually in series. So we can actually resketch a circuit like this. So you can resketch a circuit. That's 2 kilo ohm. That's 1 kilo ohm. 2 kilo ohm. 1 kilo ohm. That's going to be Rx. And that's going to be, let me call it RA. But RA equals to 2 kilo ohm. So 2 plus by RL kilo ohms. So now the question becomes whether we can, that's Vx, yeah. So basically now the question becomes whether we can choose RA such that, we can choose Rx such that the voltage Vx is independent of RA. So I think this question might be a little bit harder to get started, but the biggest hint is the fact that it's placed in the circuit theorem question, in the circuit theorem section. So what do you have in circuit theorem? So superposition, source transformation, yeah, and Thevenin/Norton and maximum power transfer. Do you see like how there's only one thing that could possibly work, which is going to be Thevenin/Norton? So the trick here is to consider replacing this part of the circuit with its Thevenin equivalent, because this is a linear circuit, right? So we're allowed to do that. So now this circuit becomes VTH. Oh, by the way, I'm just going to reverse the polarity of VTH because it just makes our calculation later easier. But remember, VTH can be negative here as well. So I'm allowed to invert the direction of the voltage source. That's going to be RTH. And oopsies. And that's going to be, wait, what's happening? Wait. Cool. That's going to be RA. And that's going to be Vx. And the ground still stays here. Okay, so now do we all agree that VTH is non-zero, right? like because we have a 20 volt here, and nothing else, and there's no dependent power source, so VTH is not going to be 0, right? Let me just write that down here. So VTH doesn't equal to 0. Cool. And what's actually VTH? We're not interested in that because we don't need it. But what we need though is the RTH. For this circuit, so let me just draw in blue whatever I circled here. So that's going to be 2 kilo ohm. That's 1 kilo ohm. That is Rx. So that's 20 volts. So do you see it? 2 kilo ohm. To find this Thevenin resistance in this case, we can just short circuit it to 20 volts. And do you see like how RTH just equals to 2 kilo ohm in parallel with 1 kilo ohm in parallel with Rx, right? Because once we short circuit the 20 volts, we only have those 3 resistors in parallel. So that's going to be our RTH. So now, let us find the expression for Vx. By the way, if you look carefully at this circuit, do you see how Vx is just a voltage across Ra? So we can use voltage division. Yeah, cool. So Vx equals to VTH times by Ra on Ra plus by RTH. That's going to be our Vx over here. Okay. So we're allowed to change Ra, right? But so we're allowed to change RTH, but we want to make sure that Vx, no matter like after we set up RTH, no matter how we change Ra, Vx stays the same. So what's the only 2 cases this can happen? The first one, VTH equals to 0. Second one, Ra such Ra plus by RTH equals to a constant. Right, because this is the only 2 cases where we're like basically when we change our Vx is able to stay constant as we change Ra around. So this is not possible, right? We have basically shown intuitively before. VTH is not going to be 0. Here's the second case. If this thing is a constant, then do you agree that RTH must be 0? Because we're allowed to change like Ra, right? No matter how we change Ra, Vx has to stay the same. So RTH must be 0 to make this thing constant 1. So if RTH equals to 0, we have 2 kilo ohm in parallel with 1 kilo ohm in parallel with Rx equals to 0. And what's the only case this can happen? Well, Rx equals to 0, right? But then we want to find a positive Rx. So this cannot happen. So yeah, there's no matter what Rx we set, the voltage Vx is always going to be dependent on RL. So cool. Is there any questions regarding this? Yeah. Yeah, yes?
I don't understand why RTH is 0.
RTH is, oh, RTH is 0, okay, cool. So in this case, right, remember we're allowed to change around, so basically when they say Vx is independent of the load RL, it means that when we change around RL, Vx is going to be constant, right? Yeah. Basically changing around RL is same as changing around RA, right? Because RA is just 2 plus by RL. Yeah. So I want to make, from this expression here, we want to make sure that no matter how we change around RA, Vx doesn't change. Yeah, so do we see like how the only way this can be done is RTH equals to 0? So in this case, Vx equals to VTH. Yeah, if RTH is not 0, then we see like how this function is not going to be constant, right? If A is not 0. So does that answer your question? Oh. Yeah, cool. So good question. Is there any other questions? Cool. Let's move on to the last question I have here. So in this case, we want to find the resistance RL such that Vx equals to 0 volts. in this case, some of them might not be the most useful thing to do, right? Because I guess it's pretty difficult to do it. The much easier way is to either use superposition or we use source transformation. I think the easiest way is to use source transformation. So let's do it, source transform. Let's transform this network into a current source in parallel with a resistor. So this becomes I12 on 2 kilo ohms, so that's 6 milliamps. In parallel with a 2 kilo ohm, that's 2 kilo ohm. And that's in parallel with the 1 kilo ohm, which is in series with the 2 kilo ohm, and then of course, I'll just show the remaining circuit up here. That's IL. 2 kilo ohm. And Vx, of course, it still stays here. Cool. So that's a new circuit we have determined from source transform. What we can do next is that we can actually start doing nodal analysis. So that's what. So remember, we want to find RL such that Vx equals to 0, right? So let's label just Vx equals to 0. That's 0 volts. So if Vx equals to 0, do you see that there's not going to be any current in here? So that's going to be 0 amps, and that's going to be 0 amps if Vx equals to 0. So right, so if 6 amps passing through here, then 6 milliamps. So 6 milliamp passes through here, then 6 milliamp also must pass through here. So we have a node here. Let's just call it what node did I call it? VA. So KCL in VA. We have, let's label this. Wait, I'll just label it in another direction for no good reason. So that's I2. And what do I have as I1 here? Oh, I already solved for I1 equals to 6 milliamp. Cool. So originally I have I1 here, but I1 equals to 6 milliamp. So KCL in VA, we have 6 milliamp plus by I2 equals to 8 milliamps. Then I2 equals to 2 milliamp. Right? Because 6 milliamp and I2 is leaving the node, while 8 milliamp is entering the node. After we have calculated I2, we see that VA just equals to 2 RL volts. So let's just write RL in kilo ohm. So in this case, we have VA just equals to 2 RL volts. Cool. After we have VA, we also know something else, right? We can do Ohm's law in the 2 kilo ohm resistor here. So I1 equals to VA minus by 0 on, what's it called, 2 kilo ohm. So 2 kilo ohm. I1 is going to be 6 milliamp, we have determined before. So VA equals to 12 volts. Cool. Yeah. If VA equals to 12 volts, we can just chuck it in this expression over here. So 12 equals to 2 RL. And RL equals to 6 kilo ohm. So that's how we can find RL in this case. Yes, any questions? Yeah.
Can't we add the current sources together and the resistors of 2 and 1 k?
I think I tried to do that. It's not really nice. It should theoretically be possible. Yeah, but it's true that I tried to like transform this as well. The answer is not really nice. Yeah, so it should work, but this is probably going to be the nicest answer, I think. Cool.
To be a bit shorter, when you get like 8 minus 6, and then the 2 kilo ohms parallel with the 1 kilo ohm. I don't know if that's possible.
Right, so it should be, yeah. I guess you can try this out later. We will have the slides ready for you guys. Yeah. So cool. It should be possible. Yeah. So any good question? Any other questions then? So cool. And just by the way, if you have, let's just quickly go back to this question. If you have not figured this out, I'll give the answer. So have any of us done Math 1081? So discrete. If so, we should have heard of something called recursion. Let us consider a circuit. So Rn, it is circuit when there is, wait, let me just, that's 1 ohm, that's 1 ohm. There's N resistors here. That's 1 ohm. So basically what I mean by that is that there, is that there are N of those vertical resistors. That's Rn, right? For Rn plus 1, we can actually add another, we just add a branch here. So that's 1 ohm, 1 ohm. So do you see like how Rn plus 1 equals to Rn in parallel with the 2 ohm here? Cool. So that's going to be 2 Rn on 2 plus by Rn. We're limiting towards infinity, right? So we can take a limit of both sides to infinity. So n towards infinity. Rn plus 1 equals to 2. Let me just write the limit here. Lim n plus n towards infinity, 2Rn, oopsies, on 2 plus by Rn. Do you see like how the limit of n towards infinity, Rn plus 1 is going to be equal to limit n towards infinity, Rn, right? So let's call it just, well, limit R. And then this is actually a quadratic equation. So R squared plus by 2R, R squared plus 2R equals to 2R. Wait, sorry, I think I missed a silly mistake. Yeah, I made a silly mistake somewhere. Yeah, the answer, by the way, I think I heard someone said the answer should theoretically be the golden ratio if you actually have calculated the limit correctly. So yeah, sorry. So yeah. Sorry. So I made some silly mistake here. So I'll now pass the mic to Leif, who will answer this question and do capacitors. Yeah.
I'm a bit tired.
Yeah,
that's good though. Look. Hello. Okay, great. Where's the pen? Wait, what? Hello. All right, guys. So I'll just finish off that question that Jerry posed. So it was just doing, where was it? It was just this, right? And we just have to find the equivalent resistance coming from the left. And this resistor ladder goes on to infinity. So one sort of key insight that you might want to see, or just if you're clever or you've seen a similar problem like this, then you might have already sort of seen it. But looking at this whole resistor ladder, one thing that you might consider is that this is actually the same thing. If you just sort of ignore the first two resistors, right, because this thing goes on to infinity, that what I've highlighted in yellow is also REQ. So really, if I wanted to, I could rewrite this circuit like this. It's just I think Jerry's way is exactly the same, but This one has a bit less notation to it. This is 1 ohm, this is 1 ohm, in parallel with a resistor, which is REQ. So it refers to itself. And so if you know the equation for, if I solve this right now, REQ is going to be equal to 1 plus the parallel connection of that 1 ohm with REQ itself. So that would be REQ over 1 plus REQ. So if I multiply that out, now you've got the constant that we were missing before. REQ squared plus REQ is equal to 1 plus REQ, it's 2 of that. So if I just rearrange, then I get REQ squared minus REQ plus 1, minus 1, my bad, is equal to 0. Now if you solve this, you'd have to complete the square because it's irrational, so you can't easily do this. But if you did solve it, you'll find that REQ is equal to 1 plus minus the square root of 5 on 2 ohms. Now, you've seen this number before, if you've done maths or something like that. This is the golden ratio. You might see this in other problems relating to the Fibonacci sequence. It's related to that between the ratios of consecutive terms. There's also another way to write this. So if you didn't want to write this recurrence this way, you can write it as a continued fraction. So you could do REQ is equal to 1 plus 1 over 1 plus 1 over 1 plus 1 over 1 plus, and then forever. That's another way to think about it. But this converges to phi. It's not too important. You're not going to get a question like this, but it's good to think about it in this sort of way. I think it's a cool problem. And you probably won't revisit this later on, so it's good to know about it now. All right, but back to the actual content. All right, so we're doing capacitors. Now, this is probably quite fresh in your minds because you've only done it maybe in the last 2 weeks. But this is the last content you'll be assessed on. You won't be assessed on RL circuits, but RL circuits are pretty much just the same as RC circuits. They're the dual of RC circuits. So if you follow the problem-solving process for RC circuits, it's the exact same for RL, just for your final. So here's a bit of theory. I'm not going to go too deep into it. Hopefully you guys know the theory. I'll just go into the questions. The 2 things to keep in mind are sort of this differential equation that describes the behavior of capacitors, right? So they're related by the change. So the current going through the capacitor is related to the voltage across it. So because of the passive sign convention, we say that this is IC going down, assuming that this is VC. And naturally, if you've got DC steady state, so if you've got some DC voltage across that capacitor, that's not changing, then the derivative is 0, and so your current is 0, which means that it's an open circuit. And so you see that come into play when we do the questions later. And then once you get to AC, which I think you might have done in your early labs, but you'll formally learn in week 8, you'll see that you'll work with impedances, and it might not be so clean, but it's not too hard. Now, if you solve this differential equation, I'm not going to do it now because for the sake of time. But in general, hopefully you've seen this in lectures. But this is sort of the general brain-dead equation to solve these sort of problems. So you don't have to really think too much about these sort of problems. As long as you've got this first order, because it's a first order differential equation, if you just stick to this formula, it will get you the answer. V infinite pretty much explains or describes the voltage across the capacitor after you've done some sort of change to it to some arbitrary time after. So I say infinite, right? But there could be another change soon after, but your circuit doesn't know that you're going to change it 5 seconds later. So it's going to consider what you're doing right now to infinity. Once I do the next question, it'll all sort of go into place. And then tau is your time constant. It's just the rate at which the thing dies, the decay. Hopefully it's quite straightforward, but yeah, sometimes it's not too easy to find. I think for the second question, it might not be so straightforward. All right, so here's the first question. This was from a past paper. The other two that I'll do, I've made myself. That'll be interesting, just quick sneak peek. So the first part, take a step back. This is the circuit. We've got two switches, right? And they both are open at first, and then they both close, or one of them closes at t equals 0, and then 0.1 seconds after, the second one closes. And so you're trying to find the sort of VC of t of those like ranges of time. So between 0 and 0.1, and then after 0.1 seconds. All right, so let's start with solving this problem. So the first part asks us to find VC of t between 0 and 0.1. So in that case, this switch right here stays open. We haven't flipped it over yet. So really, we can consider that to be open. We don't have to worry about it for this part of the question. And so what we're doing is that we're seeing what happens to the voltage across the capacitor as we're closing this. So going back to our framework, for this, where should I do it? That, right? There's really three things you have to find out. If you want to find VC of t, you need to find, one, and you find VC of 0. I'll put VC of minus. I'll maybe explain why in a second. VC of infinite, and also the time constant, which is equal to RTHC, where C is just the capacitance, which we've been given, thankfully, so I don't have to put that in. All right, so VC of 0 minus means that what is the voltage across the capacitor just before you switch on this, just before you flip the switch. Because capacitors control voltage, they're continuous and differentiable, so you won't get like a cusp when you're changing it. It doesn't change immediately. So you can say that this is also equal to just right after, but you don't have to worry about that. Right, so we can find VC of 0 first. So before this is flipped closed, so that means what we're having is that before t equals 0, our 10 kilo ohm resistor is not shorted, because after that, once we flip on the switch, well then this becomes a wire, and then this shorts the 10K. So before then, we've got the 10 kilo ohm resistor, we've got the source, and then we've got the 30 kilo ohm resistor, and then the 60 kilo ohm. So really, it's just one loop. Oh, actually, no, it's two loops. No, it is one loop, my bad. But this, I should have maybe taken a step back. This becomes an open circuit because you're assuming that you're at DC steady state. This gets getting very messy. So it's really just one loop. And so what we want to do is that we want to find the voltage across these two points. And so what that is really is that it's just a voltage divider, because we know that we've got only one source. Let me get rid of some of these ugly annotations. We know we've only got one source, and we've got, well, if we combine these in series, we've got 40 kilo ohms over here, but we actually want the voltage across the 60 kilo ohms. So if I want to solve this pretty quickly, I'd say that this is going to be 12 times, well, it's going to be over the 60 kilo ohms, and the other one's 40 kilo ohms, so that's 6 on 10. So it's 60% of 12. So that's 7.2 volts. All right, hopefully you're convinced by that result. It's just a simple voltage divider. All right, so that's before you flip on the switch. Let's say you flip on the switch. What happens then? Well, nothing much changes. What happens, right, is that once we flip this on, this part gets shorted. What we're still measuring across the 60 kilo ohm resistor is just now, instead of using 40 kilo ohms, well, now it's just 30 kilo ohms. So now it's going to be 2/3 of the voltage, right? Because we've got 60 kilo ohms here, 30 there, well, logically speaking, 2/3 would go over the larger resistor. So we would get 2/3 V infinite is going to be 12 times 2/3, which is 8. All right. So we've got those two parts pretty quickly. Maybe I should be more clear in what I'm saying. When I'm finding these two, what I'm doing is that I'm assuming that our capacitor was at steady state. So really, these are open circuits. So you don't have to consider that. Or you're measuring the voltage across it at steady state. OK. So that's those two. And now quickly to find the RTH. So when you're finding RTH across these two nodes, go looking inwards, what we know is that we're considering this after we flip the switch. So after we flip the switch, we have, well, this becomes shorted. We're turning off the source. If you go back to Thevenin's method 1 from Jerry's part, you short the source. So now you've got the 30 kilo ohm in parallel with the 60 kilo ohm across these two. Because then it will become like this. Sorry, I should redraw it. Oh, wait, there we are. This is 30K and this is 60K. And they share the same two nodes here. All right, so 30K parallel 60K, well, that's going to be 20K. Multiplied by 2 micro, which is going to be 2 micro as in the capacitance. So what's that going to be? That's going to be 0. I think I wrote it down, didn't I? I think 0.04, but I don't want to make a mistake. Oh. Yes, it is. 0.04 seconds. All right, so the answer, you just plug it into the formula that you're given. This one. So it's going to be V infinite, which is going to be 8, plus, well, then it's going to be 7.2 minus 8. So it's going to be minus, oh, I should have maybe changed that. It will be minus 0.8 e to the minus t. There is t naught here, which accounts for the time shift. Now, because we're considering when we're flipping the switch at t equals 0, well, the time shift is 0. And this is over tau volts. And tau is this one. I guess you can plug in 0.04, but the thing, it's pretty much, it's the same. All right, so that's the first part. All right, so the second part is that we have to find the energy stored at the capacitor at t equals 0.06 seconds. Oh, yeah? Sorry? Yeah? So you want to know why it's 30 parallel 60? All right, so maybe I'll redraw it, just so it's very, very clear. So we're finding the Thevenin equivalent resistance after we flip the switch. So after we flip the switch, this becomes a short. So this, we don't care about that anymore. If that's the case, if we're finding our Thevenin, why is that going like that? If we're finding our Thevenin here, right? Well, if you remember from method 1, right, we've only got independent sources. So we short this. And this is an open circuit. So you can kind of see how, if you just like follow this around, like this is your effective circuit. This is your node. Let me rub this one out. This is your other node. I haven't really drawn the resistors, but can you see that? And you can see how that's pretty much exactly the same as that. Yeah. And then you can plug it into your calculator and you get 30K parallel 60 is going to be 20. Okay. All right. So the next part is that we have to find the energy stored in the capacitor. Now, I think there's an equation for this that you're given, but I don't always remember it, so I'll derive it for you guys. Yeah, so if we want to find the energy stored in the capacitor, well, what do we know about energy? We know that energy, or work, is the derivative of power, right? And for our capacitor here, from the previous part, we're looking at this is t is less than 0.1, so this is using this previous part here. Well, we know that we've given the voltage, right? Well, we know that P is equal to IV, right? I know that IC is equal to C dV on dt, right? So if I take this result up there and I differentiate it and multiply by C, then I'll get I. Now, I'm not going to plug it in yet. What I do know is that if I did that, then I can get current in terms of voltage. So why do I want to do that? Well, I know that P is equal to IV, which is equal to dW over dt. Now I, so if I rewrite this is going to be V times C of V dash. V dash is just going to be the time derivative of V. Now, if I rearrange this, right, and I integrate, so at t0 from some t0 of dw, that's going to be, I can take out the c because capacitance is constant, and I'm integrating from t0 to t of v dash dt. Now, in the integral on the right-hand side, well, the left-hand side, this is going to be this minus that. Now, I know that I'm taking the integral of something multiplied by its derivative. So if you know maybe a reverse chain rule, you know that if I have, if I have something like this, right, and this is a function of t, well, if I differentiate that, if I d on dt that, well, then that's going to be, that 2 is going to cancel with a 5, with a half. And I'm going to get v, right? But v is a function of t, so I have to also differentiate v. So sort of like by backwards reasoning, I know what the integral would be, because I know what it should differentiate into, if that makes sense. So I know that this is going to be c times half v squared, but this is between t and t0. Okay, and then v of this will be c, will be a half c. I'll just write that the other way around. Half c of this, so it's going to be v of t squared minus v of t0 squared. All right, so that's our equation. Now, problem is that, I mean, I don't really like the way this question's been asked, is that they haven't given you like a reference point. If you're accumulating charge or energy, right, it's with respect to what time? As I expect, the question's asking you with respect to 0 energy, in which case this is going to be some t0, in which case there's no voltage and there's no previous energy inside the capacitor. If this was like 0 of t0, they told you, oh, from t equals 0, well, then you can sub that in, and then you'd get some reasonable value. You get a delta omega. But we're doing like, I think we're working in absolutes. So what that would give you, right, is that we want to actually consider when this is 0 and this is 0, in which case you get half c dv, half cv squared. So I think that's an equation that hopefully you guys have seen. But that's how it's been derived. All right. Now, we have our voltage up there, right? This one right here. Well, we want to find that when we evaluate at t is equal to 0.06. So if I just sub that in, I think I've done that here somewhere. OK, you get about 7.82, I think. Yeah. So if I take this previous equation, if I evaluate at 0.06, I get 7.82. So what I get, right, is that work at 0.06 is half times, what was the capacitance? That was Oh, I've obscured it. I think it's 2. Yeah, 2 micro. 2 micro times 7.82 squared. And off memory, I think I got something like that. Was that it? Yeah, that's about right. So you get about 6.2 times 10 to the negative 6 joules. So it's fairly straightforward. I mean, you can either go through the derivation as I have here, or you can just memorize it. I think you can just memorize this. Or you can memorize the more general form here. Yeah, but this is probably going to be only 1 or 2 marks. There you are. It's only 2 marks, so it's fairly simple. All right, so the next part is that we have to find the voltage across the capacitor after t is equal to 0.1. So try to get through this a bit quicker, shouldn't I? So for this question, here's a couple things that you want to keep in mind. The first thing is that, well, this has already been shorted. You're not going to be flipping the switch back open, right? So this becomes shorted. Now this also becomes shorted. Now, I don't really like this question because what you've done is that you've shorted your voltage source, which shouldn't happen in reality. This is a past paper question as well, which is pretty disappointing. But yeah, like, hopefully you recognize why this is wrong. You can't have 12 volts over a wire. I think in reality there's a bit of resistance inside the wire, something lab 1 or lab 2. But yeah, I think the maths works out for what we're trying to do, but just recognize it's a bad question. Okay, so if we short this, right, well, any current that we have through this, like the left side of this circuit, is just going to be going straight to ground if I set this to ground. So I've sort of like decoupled my circuit. I've split it in half. In which case, I don't have to care about the left-hand side. So really, I just have this. Now, interestingly enough, as you can see, this equivalent circuit here is just like what we found earlier when we found RTH. So RTH is going to be the same value. If I go here, I know that my RTH is going to be equal to, what was it, 20K. And our capacitance stays the same, so this is going to be 0.04. I think, yep. All right, so that's the first thing. The next thing is that, well, I know that once if I'm only considering the right-hand side and I've disconnected my power source, well then naturally as V goes to infinity, well then the capacitor is going to discharge into the circuit or into the resistances. I could just like make an open circuit here and then you realize there's no power source, so the voltage has to be 0. But hopefully it's just sort of like by inspection, it's obvious that it's 0 volts. What's different though is that while we have, so this is RTH, that's tau, VC of infinite after 0.1 is going to be 0 volts. VC of 0, well actually it's not going to be VC of 0 anymore, is it? Because now our sort of switching point is going to be T0. So really, I have to find VC of 0.06. I need to find the voltage just before you flip on the second switch. What that means, right, is that I want to find the voltage across this at 0.06. Interestingly enough, I've already done that. Oh, sorry, not 0.06. It's 0.1, isn't it? My bad. So I need to find the voltage at 0.01 or 0.1. Now, this equation holds at t is less than 0.1 or less than or equal to. It's kind of weird because you're switching into a different equation, but it's continuous, trust me. In which case, that if I take this equation and I sub in 0.1, I'll get, what was that? It was, oh, okay, that's it. Well, I've already evaluated this, but yeah, if you just sub in into t 0.1, and you know what tau is, and you know what 8 and whatever those are, you get 7.93. That's going to be at t just before 0.1, which is also the same as VC at 0.1 plus. OK. So I know all this information, so I can quickly answer by saying I know that this, so I should change that, that's not correct. This is going to be 7.92, I think, is that what I said? 0.93 volts. All right, so the answer here is going to be 7.93 e to the minus t. Now there is a time shift. T naught is going to be 0.01 or 0.1 because that's when you're doing the switching action over tau, which is the same. So yeah, that's the voltage for this part. All right, and then you have to calculate the current flowing through the 30K resistor at both intervals. So you have to use this one. It's a bit of a lengthy question. Part 2 and 1. Oh, this is it. I sort of quick scoped it. Because, I mean, because you're talking about this one, right? Well, V, it's going to be this, right? VC of 0 minus VC of infinite, right? Multiplied by E, or whatever. But this is 0, and this is 0. V infinite is equal to 0. Because you've gotten rid of your voltage, or your source. This one here. But then you can see that if you just multiply this by this, well, then you get that. Sorry, there's a lot of arrows. All right, so quickly go through this last part. I'm not going to do the full computation. I'll just give you the general answer, and then you can compute it into your calculator. But the idea is that between 0 and 0.1, at that stage, what you're saying, right, is that you've got this voltage. It's going to be 12. Actually, no, hold on. What you want to find is that you want to find this current there. Now, you know that this is going to be VC of t, right, at some arbitrary time point, right? And then here, right after you make the switching point, well, this shorts. So this is 12 volts. So if I want to find I naught, so for 0 t 0.1, well, I naught of t is going to be equal to 12 minus VC of t. This is the first one, not the second one. Be careful because there's like two different equations we have over 30K amps. And so if you just take whatever we got from part 1, this one here, and then you just sub it into there, and you just do the number crunching, that's the answer. For the second part, when we've put down both switches, so this becomes shorted as well. We know then that if this is 0 volts, sorry, let me, I mean, this is also shorted, but what happens then, by our bad circuit, this becomes 0. I know it's shorted to the 12, but ignore that. That's just a quirk of the question. If that's 0 volts, well, then it's 0 volts to VC over 30, in which case what you get is that you're going to get minus VC on 30. So for the second part of t is greater than 0.1, is going to be minus VC on 30K. All right, was that clear, hopefully? Are there any questions? Yeah?
Just a question on the tau for after the second switch.
Yeah.
How is it the same as the last tau? It is the same.
It is.
Just because
Well,
if we turned off the voltage source, it's like basically the same.
well, I mean, that's the same. Maybe a better way to think about it is what changes when you flip on the second switch, right? If I flip on the second switch, well, the first switch shorts this, right? if I flip on the second switch, well, yeah, I mean, you short this regardless, so the circuit ends up the same. All right, any other questions, or should I just move on to a more difficult one? No? All right. No hands up? All right, so this is a funky circuit, but it's not too bad. It looks a bit intimidating, but it's not too bad. You can exploit a good bit of symmetry in this, so it comes out pretty nicely. All right, we're all leaving at once. Great. All right, so let's consider this. All this question is asking is find VC and IR. What this tells you is that before at t equals 0, this source is connected, and this one is not connected. And then when you make the switch, this one goes up here, and this one connects this voltage source. So what you're doing is that, gee, okay, everyone's leaving. All right, so at t equals 0, or before t equals 0, you've connected this 10 volt, and then after, you've connected this 5 volt. And then you're getting rid of one, and you're adding on the next. All right. So the algorithm to follow to solve this sort of problem is essentially the same. We know that for t is less than 0, or less than or equal to, sure. We want to find VC of 0 minus, right? At that stage, we know that this is connected there. So this is 10. This connects there. So this is 0 volts. So now we've got 10 volts across this. Now it looks a bit awkward, but if you think about it, it's sort of like overlapping voltages, right? That all follow KVL. What I know is that taking any path, right? Sure, I should have been maybe a bit more explicit. This naturally becomes an open circuit. Right? This becomes an open circuit. From here, down here, you get to 0 volts. But also, from here, down to there, we get to 0 volts. Right? And there's no current going in through there. So what that tells you, I mean, I picked the numbers conveniently to be 4 and 2. If you take your 10 volts, right, you can do 2 voltage dividers. I know that the voltage, let me get rid of some of these ugly annotations. I know that this 10 volts, right, 2/3 of it will go through there. And because, well, that's 4 and that's 2, and then 1/3 of it will go there. I also know, symmetrically, that 1/3 of the voltage will go through there, and 2/3 will go through there. So if I'm going down from 10 to 0, and this is 1/3, and this is 1/3, well, this has to be 1/3 of the voltage. Sorry, this is all multiplied by 10. Maybe a bit more explicit. Make sense? Hopefully? Sorry? Which ones are in parallel? They're not in parallel, they're actually in series. Well, actually, those two, the green and the light blue, are in parallel with each other, right? But the blue, like that path is in series. Because the middle part is on the open circuit. So without even number crunching with KVL, I can tell you right now that the middle part's going to be 10 on 3. From plus to minus. All right. So that's the first part. Oh, that's not nice. Okay, now if I check for V infinite, oh sorry, yeah, so after this, so I have to check the other case, right? What this tells you is that now I'm connecting this and I'm disconnecting that. So this becomes 5 volts and this becomes 0. Because it gets shorted. Or not shorted, but disconnected. Now this problem, I mean, symmetrically is the same, right? Because any voltage I've got there, well, 2/3 is here, 1/3 is there, 2/3 is there, 1/3 is there. Well, then logically, there's only 1/3 going through the middle. The only difference though is that now this is the polarities. I mean, I've defined them this way, but I'm putting in my 5 volt from the right, so I'm flipping the negative, essentially. So really this answer is 5 on 3, or negative 5 on 3. Are there any questions about that? Hopefully it's pretty clear. The next thing, we're going a bit over time, but it's fine. I've booked this room till 3, so. All right, so the next part was I have to find tau, which is RTHC. Now we're given C, but we haven't been given RTH, so we have to find that. Now, to find RTH, it might be a bit awkward to look at, but as long as you stick to your like formal laws of how things are connected in parallel and series, it's not too bad. Pretty much, what I say is that if I want to find RTH, right, RTH after, so in this case, when this is connected and this is connected this way, well, to find out RTH from here, from the middle, right, I can short this source. And so what the circuit looks like now, right, is that I've got this. Yep. And then this connects like this. Yep. And this is 2, and this is 4, and this is 2, and this is 4. Okay, and you find RTH in the middle. All right, now this looks kind of wacky, but what I do know, right, you just have a look at it. What's hidden is that this resistor here, right, sorry, have I drawn this incorrectly? No. No, yeah, no, it's fine. My bad. This node here, right, and this node there, what do they connect to? Well, they connect, I'm sort of like just giving you the answer. It's sort of hard to see, right? But what you can see is that this resistor here is in parallel with this one. And the reason for that is that if you look at the blue nodes, right, this one connects like this, which is the same as this. And this orange, there. Can you see how they're in parallel? Okay. So what that tells me is that I can simplify this. Well, why did I rub it all out? Okay, that's fine. Wait, actually, there we are. That's better. So if I simplify the circuit now, okay, what it will become is something like this. Wait, so that becomes in parallel with this, which is 2. Okay, so that's 2. You get something like this. So I've absorbed that parallel network into this middle node, or this middle thing. This becomes 4 parallel 2, because I was connecting this one and this one, and this becomes 2. And now from here, you can see that this 2 is also in parallel with the other one. Now, why does that make sense? Well, this circuit is symmetric, right? If I flip this vertically, it's the same thing. So logically, it will be this, like the same parallel network. So you've got 2 pairs of 4 parallel 2, and then when you simplify them, well, they're just in series after that. So RTH will equal 4 parallel 2 plus 4 parallel 2. Are there any questions about why that's correct? It's not very maybe it's not that obvious, but it's just because like the symmetry in the question, and you just sort of have to like be strong in your fundamentals of if 2 things are in parallel, well, they share the same 2 nodes on either side. If they're in series, they only share 1 node. Okay. So just to finish off this question, actually no, I have to find the current after. Okay. So if I want to find the voltage, well, it's just the same formula, isn't it? V infinite, we need V infinite is going to be minus 5 on 3 plus it's going to be 10 on 3 minus 5 on 3, so this is plus 5 on 3 e to the minus t on tau I didn't even calculate tau. Well, it's just going to be 2 times 4 parallel 2 times C, which is 3 milli. Now, I'm not going to number crunch it for you guys. But yeah, you just plug that right in, and then there's your answer for V. Well, I dropped my pen. Not too bad. Now, we have to find the current going through this, which is less nice. So what we have to do is that we have to consider, right, at t is greater than 0, we're considering the circuit when this is connected and this is connected this way. Now, I know that this, actually, let me change the color here. I did not change the color. There we are. So we've got this. Now, I can make up a node. I can label a node. I'll say this is V1, sure. And I know that this here is 0 volts. If I want to find the current IR, well, it would be helpful if I know the voltage across this from these two nodes. Yeah? So I know, right, that the voltage across this 4 ohm resistor is going to be given by these two. So what is that? Well, I can tell you that that is going, well, this is 5 volts. Why? This is 5 volts at this point. Well, then we know that our V4 volts, 4 ohms, sorry, is going to be 5 minus V1. So that gives you the voltage across this. But then this is negative, but we don't want that because current is going this way. Sorry, it's a lot of double negatives. So it flips. So what we want is that we want to subtract VC. So that is going to be voltage, or V, of 4 ohms. Now the current is just going to be divided by 4 of that. So IR of T is going to be 5 minus V1 minus VC on 4. Is that clear-ish? Now, what's good is that we know what VC is. I'm not going to plug it in because it's not like really big. But we know what VC is. We don't know what V1 is. So we have to find what V1 is. Well, as soon as we know what V1 is, well, then we get IR for free. Well, not for free. We already did the work. But you get the answer. It just pops out. So what is V1? Wait, sorry. I need to check. Yeah, no. That's fine. It's OK. All right. So if I want to find what V1 is, all I have to do is just do KVL across any length. It's a symmetric problem, so it won't matter where you do the length or the path through. But I'll just do the top one. Why did I rub that out? If I wanted to do KVL across this, I know there's 0 volts. I know that this is 5 volts up here. This, I've defined that to be V2. Oh, sorry, V1. My bad. So I know that V1 of 5 minus V1 on 2, that's going to be the current going in through there, right? Oh, sorry. Yeah. 5 minus V1 is going to be the current going through there, right? Plus, I should probably define it a better way. All right, let's just say that all currents going into a node are positive and all currents going out of a node are negative. In which case that this current going into the node is positive. This current going through there is going to be negative, and this current here is going to be negative. So this top one is going to be minus V1 on 4, because it's going from V1 to 0. And it's also going to be minus the current going through the capacitor. Now the current through the capacitor is going to be the derivative of this multiplied by C, right? So whatever that was, that's going to be, well, that's going to be 15 on 3, which is 5. So that's going to be so IC is going to be minus 5c on tau e to the minus t on tau. So all I've done is I've differentiated it, and then I've taken the exponent down, and then I've sort of skipped a step, but I've also multiplied it by c. So that's your equation for IC, and that's going to be minus IC is equal to 0. Well, that's good. Now I have V1 in terms of IC. And I know what IC is, and I know what VC is, so I can plug them into this, and then I get IR of T. Now I don't want to, I think I should move on to the next question because it's just number crunching. But if I sort of do a bit of algebra, what I'll get, I'll just copy down what this was. I'll find that I'll say, well, I know that from here, V1 is equal to 10 on 3 plus 4 on 3 IC, which is, yeah. And then I can substitute this into here, which gives me that IR of T is going to be 5 on 3 minus 20 C on tau e to the minus T on tau. Okay. And yeah, that's pretty much how you get the second part. It's a bit tedious. It's not hard, but it's just tedious. Are there any questions on that before I go to the last question? The last question is probably the most interesting one. No? Okay, great. Are there any questions on the thing? No. All right, last question. So this question is an RC circuit. We've got 2 diodes in it. Now, you guys probably, I mean, you should know how to be able to do this, but you probably, it's unlikely-ish you might get a question like this. But it's good for future courses. It's pretty useful. Pretty much, all you have to find in this question is that you have to find the time constant observed by this. So it's really the same, like question 1, part 2 are sort of like 1. Because if you find VC, well, you need the RTH, so you can find the time constant. One thing that you have to keep in mind, or one sort of definition for your diodes, right, is that this is essentially a source. Hopefully that was covered for you guys in week 1. All right, so if I want to find the time constant from the, just before the switch is closed. Okay, sorry. I should also maybe specify the switch action. So when the switch is closed. Okay, so it's closed here. It's not open. It's a deceiving circuit. And then later on, I open it. So it's like this at like t equals 0. So it opens up. All right, so I want to find RTH. What that tells you is that, well, I'm checking RTH from here. This becomes shorted. Now these 2 diodes are also sources, essentially. So they get shorted. And so what you get, really, is that you get 1 loop. Oh, no, you don't. You get 2 resistors in parallel. Because what this pretty much comes down to is this. This is 50 ohms, and this is 300 ohms. So yeah, you're just shorting all the sources, and then you get 2 resistors in parallel. And so that tells you that RTH is equal to this, which is that, I think. Yes, yeah, that's right. All right, so that's RTH. All right, so now for VC. So we already found RTH. So I can already give you tau. Tau is going to be RTH times C. which is, what's C? C is 5. Okay, that's interesting. Also, it's good to have a bit of intuition about your values. 5 farads for a capacitor is very, very high. If you were working in your labs, most of the capacitors you're working with are what? A couple nanofarads or a couple microfarads. So 5 is really, really big. And I mean, if I did the calculation, this is going to be, this is 300 on 7 times 5, which is what? 1500 on 7, which is, well, it's about a bit over 200. We'll call it 200, yeah, like, I'll just say 200. Damn. Now, this is 200 seconds time constant. So what's that, 2 minutes? No, 3 minutes. This is a bit over, like, it will take you a bit over 3 minutes for your circuit to discharge, which is quite a long time, which you'll see maybe in your next lab if you do RC circuits. So weird values, but it's good to maybe like have a look at your values and see if an answer is reasonable or not. So that's tau. For your time before, so hold on. So before I open this is opened, or I'm checking for the voltage across this. All right. Now, what I do know, right, is that this circuit becomes one loop. It becomes this plus minus, this is 12. This is 300 ohms. This is the diode. This is what you're trying to measure across. And this is 50. So all you have to do is just do one mesh. Sorry, why did I do 1.7 ohms, 1.7 volts? So if you just do one mesh, right, you do minus 12 plus 300. We'll call this some sort of I. 300 I plus 2 times 1.7 plus 50 I is equal to 0. So you got some equation for I. I did calculate that earlier. I think the answer was 0.02. Yeah. So if you solve for this, you get I going around this loop is 0.02. That's not what we want to find. We want to find this. So what is that? Well, it's going to be whatever voltage it takes to get up here plus 1.7 to go back up and then come back down the loop. So what is that? That's going to be V is equal to 50 times 0.02 plus 1.7, which is, what did I get? Okay, 1.82. And that's VC of O0, V of 0. Does that make sense, hopefully? So it's just a bit of mesh, that's all it is. All right, so now for the second part, which is quite the weirdest part for this question, is that when we open this, right, so we're looking now at VC of infinite, right, to get the rest of our equation. This becomes opened, right? So we're disconnecting our source, right? So therefore, this diode is no longer forward biased. So this is excluded. So really, all you have is this part of the circuit left. And there's going to be some VC. Initially, at 0, that's going to be 1.8, what was it? 1.82. Now, when we're finding V of infinite, we're assuming that this is at steady state. So this becomes an open circuit. Now, the weird part is that if this is an open circuit, well, there's nothing on the left-hand side. There's no current going through it, going through the circuit, right? But there is a diode there, right? That if there is no current through it, well, then it becomes an open circuit. So it's like a nonlinear differential equation. What that tells you is that you've got 1.87 volts here, right? Naturally, right, if you have no source connected to that 1.87 volts, well, then it's slowly going to decay to 0 volts, right? However, by the time, once that 1.87 volts gets down to 1.7, so when this, let's just say after some time, right, it goes down to 1.7, well then there's going to be no net current going through the diode. So it reverse biases and then becomes an open circuit. Now what happens then? You have to have maybe a bit of physics knowledge, which is, I don't know if you guys have taken Phys 1B. Well, you don't really need to. But the idea is that if this diode reverse biases, right, what you're doing is that you're shutting off the capacitor and you're pretty much removing it from the rest of the circuit. So this capacitor has nothing to discharge into. So ideally, it'll stay at 1.7 volts, if that makes sense. Because what is a capacitor essentially? It's just the store of charge, isn't it? Right? It's like a temporary temporary source, right? So you charge it up, and then it discharges 1.7, and then the diode reverses, right? And what it does is that the technical word is that it clamps the voltage at 1.7. So really, this answer is 1.7 volts. And this current will be 0, so there's no voltage across that. So really, you're measuring this. And this is 1.7 volts. So it's a bit weird. You have to use a bit of like intuition. It's not like rote learning, this question. So it's pretty good. If I was your lecturer, I would include a question like this. But yeah, so this diode pretty much clamps the voltage at 1.7 volts instead of making it letting it decay to 0. Now, in reality, it will go down to 0 because, if you leave a capacitor down on your table, eventually it will go down to 0 because there's resistance in the air, and so it can lose energy that way or some other non-ideality. But ideally, it goes to 1.7. So yeah, and then the answer is trivially just sort of reusing the same equation here. I'm not going to plug it in. You've got the values here. This, and this, whatever that weird value. VC of infinite, this. So you just plug those in, and that's the answer. Are there any questions about that? We're about 30 minutes over time. But that's pretty much it. We're done. Hopefully you guys found that useful. If you came a bit later, we had wait, did I have a last slide? No, I didn't. We did have a QR code at the start. If you haven't done that, please do that, just so that we know how many people came. Half the people left when I was talking, so maybe that's unfortunate. But yeah, thank you all for coming. Best of luck for your midterm. And yeah, if you have any questions, you can come up to the front and I can answer them. All right, bye-bye. It won't be on Moodle, but I can put it as I can put a link at the bottom of the stream because it's being streamed. So you can go to the description and then I'll link the actual slides here, annotated. Yeah, it's a YouTube stream. This? It's on our ELSOC YouTube. So just go UNSW ELSOC, you'll find our YouTube channel.
Thank you.
No worries. All right, let's.
I think your camera stopped working halfway through. Did you just end stream?
It died?
Yep.
I'll export the file.
Yeah, wait, let me end stream. No worries.